For decades, physics has been locked in a structural contradiction. General relativity models space and time as a continuous, smooth surface. But if we zoom in, quantum mechanics dictates that energy and matter exist only in discrete, quantized packets. Calculations that work for the cosmos break when applied to the subatomic. There is no existing mathematical bridge between a smooth surface and a pixelated grid. This incompatibility is the reason a unified theory has eluded researchers for over a century. The continuous model relies on the metric tensor, the mathematical engine behind Albert Einstein's formulation of gravity. Meanwhile, the microscopic world is governed by probabilistic wave functions, pioneered by Erwin Schrödinger. The two frameworks describe the same universe using completely incompatible languages. The Gibson framework resolves this by abandoning continuous mathematics. Instead of a smooth fabric, it proposes that reality operates on a deterministic computational architecture, a discrete grid processing information. This architecture is configuration space, a pristine three-dimensional lattice of discrete spatial units called s-particles. At every tick of Planck time, this grid computes local rules. The output of these trillions of microcalculations is the physical reality we perceive in rendered space. If spacetime operates as an active, localized computational grid, then phenomena like gravity and electromagnetism are the emergent outputs of its underlying algorithm. To understand this algorithm, we look at this structural unit, a central s-particle connected to exactly four neighbors. The system operates on what is called t-transfer. To advance in state, s-particles must exchange t-particles, which function as discrete tokens of time. This exchange is governed by the full complement rule. An s-particle can only render its next state into physical reality if it successfully receives a t-token from all four of its neighbors simultaneously. But local conditions disrupt this synchrony. High velocity or the presence of dense mass creates a lag. If a token arrives late, the central node experiences a data deficit. It freezes in its current state, waiting for the missing information to complete the computation. When a deficit occurs, the delay propagates. The adjacent nodes must also wait, creating a cascading mechanical stutter across that local region of the matrix. What we observe as physical laws are the macroscopic effects of this localized computational lag. The stalling of the grid is the mechanical cause of both time dilation and gravity. We can test this mechanism directly against known relativistic effects. Consider the precise time dilation experienced by the International Space Station as it orbits the Earth. Classical physics models this using the Lorentz factor. As illustrated here, Einsteinian mechanics dictate that high velocity curves the flow of time itself relative to an observer on the ground. On the right, the Gibsonian model derives the exact same mathematical result through discrete mechanics. As an object moves rapidly across the grid, it physically outpaces the t-tokens arriving from its trailing neighbors. This structural delay slows the object's internal clock. This identical computational bottleneck accounts for gravity. We see this clearly when examining gravitational lensing, specifically the historic 1919 solar eclipse observation that first measured starlight bending around the sun. The exact measurements captured by Sir Arthur Eddington provided the critical proof for general relativity. The conventional interpretation, seen on the left, attributes this path deflection to mass creating a geometric warping in the vacuum of space, drawing the light inward like a funnel. The Gibsonian interpretation on the right removes the geometric funnel. Instead, the sun's massive cluster of s-particles monopolizes local data, creating dense token deficits. As light navigates this congested region, the lag incrementally recalculates its trajectory angle at each specific node. Both models yield the exact same observational numbers. However, the Gibsonian framework grounds the math in physical, localized data bottlenecks rather than relying on invisible curvature. Because this mechanism does not rely on macroscopic geometric curvature, it scales down to the subatomic realm. We can apply it directly to the simplest atomic structure, the hydrogen s orbital. Early quantum pioneers like Niels Bohr mapped the energy levels of electrons, but struggled to identify their exact physical locations. Here we see the modern contrast. The standard Schrödinger model on the left defines the electron as a fuzzy cloud of probabilities. The Gibsonian model on the right eliminates the probability cloud entirely. The electron is a discrete particle, and its position is dictated by a rapid, precise, algorithmic oscillation determined by token distribution. If electron position is deterministic, we must confront the ultimate stress test of quantum theory, wave-particle duality, famously demonstrated by the double-slit experiment. The classical interpretation suggests a single particle splits into a wave, passing through both slits simultaneously to create this distinct interference pattern on the screen. The grid offers a mechanical solution. As shown here, the particle never splits into a wave. Instead, the physical slits in the barrier alter the lattice topology, creating token deficits in the surrounding empty space. These cascading deficits systematically nudge the single particle, routing it into the exact same final pattern. Furthermore, light particles evade T-tokens during transit. Because they never collect time tokens, they exist in an eternal now state, allowing the grid to instantly process these spatial updates and lock in the trajectory. By replacing the concept of non-local wave function collapse with strict local grid logic, the framework removes the primary mathematical barrier separating quantum mechanics from macroscopic relativity. Zooming out from these microscopic interactions, we observe how the stark computational wireframe of configuration space compiles into the vast, observable illusion of the cosmos. This brings us to the outer limits of the framework, the Pandora's Pyramid extended model. It applies grid logic to the cosmological scale, offering a mechanical explanation for the expansion of the universe. The model hypothesizes a specific threshold behavior. During a configuration tick, if an S unit attempts to distribute a token but fails to find a connecting bond in the grid, the excess time token spontaneously converts into a new physical spatial unit. This mechanism allows the grid to generate its own expansion wherever it encounters a computational gap. Under these rules, the growth of the universe is a structural byproduct of the lattice maintaining its own geometry. Carl Sagan famously noted that to bake an apple pie from scratch, you must first invent the universe. We are finally isolating the actual recipe. By stripping away continuous abstraction, we reveal a universe built on finite, discrete variables executing perfect mathematical iterations. The physical universe, as an information processing system, is governed by a local algorithm. Identifying that code offers the potential to move beyond observation and toward direct technical application of the system's own rules.